Welcome back, guys. So today, where did we leave off last week? I remember patching up things. In general, just to bring things together from the previous projects that we have done, like the interrupts and the scheduler example. I think we just brought things from those projects into the main MMU project. And here, let's take a look at our came in and see how much we have done. And yeah, so we have the allocate main that's still allocated as a global thing. I think it's fine because we have a special segment within our process that will hold this bitmap array, so that should be fine. And we have some two random user processes, and we have the task struct, and this is going to be internally using our kmalloc to allocate stuff. So we are allocating the task, and we are allocating memory for the k stack and the user stack, and then we are finally and we are putting the actual context, because context is the PCB in our case. So it's gonna have all the registers saved, it's gonna have the special registers, and it's gonna have the next I guess in general it's just going to have all the registers, nothing much. And that's our context. Maybe you could just look into it once. Yeah, it's just going to take the x31 register and the special registers, nothing much. So, and we are putting it in top of the kernel stack, not the user stack. So we bring down the kernel stack, and we just dereference that memory as context, and then we build that context, which is just assigning those values to null, I suppose. It's declaration definition. Yeah, so we just allocate, because SPLEL0 is the top of the stack pointer, and ELR EL1 is the as soon as we come out of an interrupt, this is what we jump into this memory address. And ESPLEL1 is just the special registers, the overflow and stuff like that, I guess. So we just set it to default. Okay, that's good. And we are scheduling one task to the queue, schedule ready queue. And we also have the init allocation map. What does this do? I guess this is old story. It's just taking the memory, and we don't have to go through it again. And we have the kmalloc in function signature. So let's come to our kmain. We are initting UART, we have some print messages, and then we are initting the GIC. As I mentioned in the previous week, GIC will act as the intermediate between the actual CPU and the devices. Every device can register its interrupt into GIC, and GIC will decide which interrupt gets to be actually sent to the CPU. And so we are gonna init that. And we also have the timer init. Timer init is supposed to be the actually we registering that GIC is gonna keep on getting timer interrupts, and it's going to work on 1 kilohertz, I suppose. And then what do we have? And we actually allocate the bitmap. That's all stuff. And yeah, rest is just test cases. Now let's come back to our to do. So initially, this is what we want to achieve. We have a user process that's going to call a lock mem with some bytes, and it's going to go through the syscall, and the syscall is going to have a number and the actual input to the syscall, input arguments to the syscall. And then we have we just gonna store the context and jump into the handler, and this part is yet to be defined, I guess, because we still don't have the syscall handler code. And then we just call the kmalloc and return that to restore the context and return it. So what we have done is we have initiated tasks, we have started the scheduler, we have set up the vector table with the tick, set up the we have to set up the vector table with the schedule on tick, and then we have to set up the vector table with user space interrupts. We need a handle that will check the syscall code. Okay, this is what we need to do. Okay, let's see. It has the code. Okay, let's see. Let's go into our vector and let's check this out. So as soon as the in general we need two different interrupt handlers. The one that's going to handle the interrupts from the user space, and the one that's going to handle in general all IIQ, in general all what's that, hard IIQs, I suppose. No, they're supposed to be the IIQ. It's synchronous and normal IIQ, so it's going to support the normal IIQs. So that way we need the, I guess, what have we written so far? I guess EL0 and it's EL1. Maybe we can write EL0 sync entry when we don't really have EL0 physical IIQs, but we have EL1 physical IIQs, and I'm not sure we are gonna call any syscall within EL1. Maybe because we are already inside an EL1, and if something comes up, then we need to be in EL1 sync entry. Maybe that's the use case. But right now, what we have to implement is this part. What the fuck happened? We need something is not working. Okay, now it works. We need this to be done, and we need this to be done. This to be done. Okay, let's check the actual implementation. If we check it, okay, we have something called IRQ dispatcher. Let's write this code, and we have set it to extend, so we can write it inside. Do we have any handlers? Okay, we have handlers. Okay, this is schedule handler. Do we have to have it as common handler? Yeah, maybe it would be better if we can write a new thing. Close this, write this, and it should be handlers. Let's see. And what are we gonna write here? What exactly do we need? Let's just define it, and then we can think about writing it down. We need a function that can switch, that can check the current IIQ and call its respective handler. This is what we need. Okay, so let's write it. And it's a void, so we're not returning anything. Let's what we need. We're not returning anything, so let's move this into here. So we have both things on our screen, and we need this IRQ defined, IRQ dispatcher, IRQ dispatcher patcher. And does it take any inputs? Let's see. This and it's going to be we save the context on top of the stack, and we are saying the top of the stack into x0, which will be our first argument. So we are going to take an context as the argument. Context. Okay, that's good. Now let's also just import that, so it should be better. It should write things. Include where does context lie? Because context is in this main. Okay, so we have the context. Now what do we do? We still have to figure out what exactly is this IRQ. How do we do that? We need to connect to GIC and check the current. What is that? We check the current code. Yeah, that's what we need to do. Let's go back to our simple scheduler. Here we should be able to see the code somewhere in handlers. No. Then where do we see it? IIQ? No. Timer. Within timer probably. Yeah. No, inside timer we're just enabling timer here. Yeah, I don't think we have this code here. Let's go back to our interrupts example. Here we should find it. It's probably inside timers.c. Yeah, we have it here. And as you can see, all we have to do is that call acknowledge. Acknowledge is going to return the value, and we can use different bit operations to figure out whether because if we and the output with this value, and we get something, and if this value is 27, then it's IRQ, timer IRQ. And in general we are going to handle this one case. So maybe what we can do is let's go back to the end. End, Control V, and we can copy this damn thing, yank it, and come back to our handler code, paste it here, and that should be almost everything. But in general, instead of having it as if condition, what we can do is make it bit modular, and what we can do is write a switch statement, switch ID, and that should be it. And if the case is 27, we put an UART, not UART puts, you should have UART printf, uprintf, or what is the name of it? I think it's, what's the name of it? UART printf, and we just say timer IRQ handler fired, and this is going to be a annoying message because it's gonna just spam our log. So just to be sure, if it's working, we can have it, and then we can comment it out, and we can call the function actually timer IIQ handle. This is not yet defined. We can define it here. Void timer IIQ handle, and it's not going to do anything. It's just empty. It instead, but let's just have volatile int equal to 1 plus 1. Just to have this function, if not, my compiler might just fucking remove it, and we can break. Question is, we break out of it, do we have to return anything? That's the biggest question. Does IRQ expect something to be here? Let's check the code where we should be in the vectors. Here, we call it, and we just move the top of the stack, so it's just expecting the already stored value to be here, and it's just restoring it. So I believe we if the stack frame starts here and should end here, it should all be done automatically. So I believe there's nothing that we have to do. Let's remove this, and what we have done is we just call the GIC acknowledge, and if you go into the GIC acknowledge code, you would see it's just gonna read from the GIC D register, I suppose, that we can just get what's the current register IRQ, and then we do some bit operations to get it into ID value, and then we just we can remove those, and then we just call the switch statement, and if it's 27, we go to thread, and then let's also add a default case that simply is going to break. Future codes can be added here. Adds to do adds future IQ and less here. Okay. And then we are done with that IRQ. Nothing much. I think that is all. there's literally nothing else. Actually, we can use this context. When do we actually want to use this context? Probably if we are within the. Mm, yeah, actually, we should. We might wanna use this here. So yeah, I just remembered it because in our case, what we are gonna do is that in every um, timer interrupt, we are gonna call the schedule too. We are not just gonna call timer IIQ handler. We are also gonna call this schedule. What is it? Schedule on click. Is this what we have defined? Let's go to definition. Let's go to definition. What the crap? Probably it's somewhere. We'll go check it. Oh, schedule on tick. This is what we want. We also need to call schedule on tick. Why? What does that mean actually? Because it's just going to say that let's say we have a timer interrupt fired. That just means we reached the 1 millisecond gap. Now the timer is fired. Now we want to schedule our actual scheduler, because in a multi process environment, that if we want to run multiple processes, someone has to decide, and it's our scheduler, and our scheduler code is the schedule on tick, and we call it whenever we fire this interrupt. And if and it's gonna take a context, and it's also gonna return a context. So we also have to make sure context equals context. So in case if the current process is time slice is over and we reach this code, this schedule on tick is gonna change, and it's gonna return a new context, and the new context will actually be restored, and it's gonna start executing. And in case the time slice hasn't been done, then in that case we would just return the same context, and we can just go on about it. And I think we could also just go through what schedule on tick does. Let's see. Why did I even take this ID value then? Did I use it anywhere within the code? Nope. That's just shame. I think we don't need this. So we do the same thing. We acknowledge. Actually, we don't have to do this because we are doing that in this part. So probably because last time instead of the IRQ dispatcher, instead of having that one indirection, I was directly using schedule on tick as the actual interrupt handler. So that's why I have this code here. We could just remove these parts, and we are setting next task equal to 0, and we also don't need this because we are going to call it here. We can do the same thing for this and this, and also for this. So current, I suppose, is a global variable. And do we want to have it like this? Maybe I can move it to Kernel and I think these through it's not really dynamic. They are just gonna have some pointers and putting that into read only. No, it's not. It's under the data segments. Shouldn't be an issue. Okay, I think it's fine. And our current time slice is 10,000, and we have three global variables that are going to take argue head, argue tail, and the current. So inside our schedule on tick, we check the current and the current state. If the current state is running, then we store the current state equal to TF. What the fuck is TF? Why do we have to store it? Because the current context would already be the same context. Maybe I don't know why I have done that. Probably I don't know. Let's see. Let's just keep it as it is. And then we check if the current time slice is greater than 0. If it's greater than 0, we just remove it, decrement it 1, and then we set the timer to fire again. This needs to be done because it's like once the timer interrupt has arrived, you have to rearm it. It's like firing bullets. You fire one and you have to rearm the bullet and fire again. So you set it again and then you just return the current context. But in case the time slice over, the time slice is 0, then we don't do this. We come down, we reset things. We set the time slice to the 10,000, and then we set the state to ready, and we say push it back to the queue. Nothing much. That's all we do. And then we come down, we pop from the queue. That would be the next process, because in my case the actual scheduling algorithm is just round robin, so it's whoever came first is just gonna be executed, and every other person is gonna be in the end of the queue, so we just go round robin. And so we check the next, we check the current. What the fuck? We check if there's no next. Okay, in case there's no next, so in case there's no one else waiting for somewhat to do, in that case then we check if the current is already there, and then we just ask them to run because nobody else is there in the queue, so you can run. If there is no next and there is no current, then nothing else to be done. You simply fire it again and you just return the same context. Probably this is going to be a disaster someday. Let's write down this disaster. Now that I think about it, I can feel that it's gonna be a disaster someday. We are returning a context that might have already be already might be or should be, could have been removed. Context who is context as already removed, possibly, because this is one of the key issues of it is lifetime bug, probably, because as I mentioned, the context is stored within a task's kernel within a task's kernel stack stop. So if the task is already removed, and if we hold this pointer, then we have an pointer that is pointing to garbage. And this is exactly what a lifetime bug is, and this is what Rust is trying to solve. But if we can use some of our brain and write stuff properly, we don't need fucking Rust. We could just do it with C. But as you know, as the code grows, the developer may not always be able to think about everything. We might miss a small small stuffs and we might actually forget it, because just like I did, and I'm just returning a stale pointer, because if I am reaching this point, that means there is no next and there is no current, and I'm still returning a context. Then whose context is that? It's nobody's, but still I'm returning. So probably I should be returning null here. Maybe return null. Perhaps maybe return null here. To do. Let's add the to do here. But whenever you learn Rust, they don't really talk about lifetimes in this way, because when I first got into Rust, maybe back in 2021, lifetimes seemed so fucking annoying, and I mean, like, I was not able to completely grasp what I was trying to learn. I mean, I was getting the point that if I pull, it's like, let's say you define a struct like this, and you put something, I don't remember anything, but let's test it. If this is what you write, and you say const mutable t, if this is what your struct is, and let's say, I guess this is how you define lifetimes, and you define a lifetime as what can you write, life file 1, and if this was your lifetime, maybe if we write it inside a rs file, it would feel a little more test.rs. Okay, so this is your lifetime. If we have a file called test, struct called test, and it has a lifetime of this. And I think if you have variables, you can also share that lifetime, bind that lifetime to this. In that case, what you are trying to say is that as long as this test is alive, the value within that struct should also be alive, and it should never be dropped. This is what you are trying to say, and by defining this extra stuff, your compiler can actually do the arithmetic operations and go through those things and see, is there any other path where this can go wrong. This is the only thing that Rust compiler does, and this lifetime is completely an compile time abstraction, and it's really good way to do it. But still the way they teach it in the books, or maybe even in the Rust example, I didn't really understand it, because let's see Rust lifetimes. Because if you are directly getting into Rust, and if you think about lifetimes, it's complete nonsense. But if you think about lifetimes from the sense, or from the examples of C or C++, it would make real sense, because this is a perfect example of a lifetime. You have a context that has a lifetime, and you just checked that that does not even exist anymore. At least at this point that does not exist, and you are still holding on to it. So what does that mean? You're just holding on to something that does not exist, or it has been already removed. But if you have a pointer to it, that means you can dereference it, and you cause a really fucking use after free error, or you might just dereference a null pointer. If you check this example, can we understand anything here? This is what the first time I saw it. So we have a integer variable that is 3, and we have a scope, so we are borrowing a reference to that I, and we printing it, and the scope ends here. That means you are dropping this fucking thing. Now you are again borrowing it, and you are dropping that, and the actual lifetime of this I ends here. What happens if we write something like I equal to null here and use it here? Then you are let's say you pass this to a thread, and you just pass that I as a reference to a thread, and within the thread the thread just deallocated that location, and the next line you are still using a reference to that I. This is exactly the issue, and if you tag it with something like this tags, compiler will find it. Compiler will say that this has a lifetime of this and you have passed it somewhere else, and the someone has already dropped it, so you cannot drop it here, or you cannot even use it here. I guess Rust does not even allow you to use it here, because it will say that you are holding onto a reference that is already passed somewhere, you cannot use it again, something like that. And to mm, get get around it, you will have to use reference counting, or you have to use arc. That's just huge fucking annoying stuff. Yeah. But also one more thing that I didn't really like the way they just simply put A and B. And when I first learned that, I thought that we need to tag things like A and B, and they are some sort of variable names or things. But actually it's just you can just call it anything, and having an actual name to it actually feels more good, because let's say this is holding a file or fd, then you can actually say that it's a file, and it's more readable, and you know that file is the actual lifetime, and it has to be alive for this time, this total time, something like that. Yeah, that's the only thing I didn't like about it. And also, I really hate writing lifetimes in Rust. It's just so fucking annoying. And it's so much better to just throw pointers and say, make sure you don't fuck it. And this is what we do here. We just throw context pointers, and we have several conditions to not fuck things up, and still we fuck it up by sending it back. Yeah, that's what we do. Well, at least now I have a to do, so probably in case, so if something happens, I can come back and check and see. And yeah, let's see if the next has something, then we don't even care about this code. We just go, we set the next thread to running, and current equal to next. What the fuck? Okay, current is the global variable, so we set it to next, and we put some print messages, we fire the timer, and we return the context. My scheduler code is so fucking simple. It's just going to do simple round robin, and I don't think I have covered many edge cases here, but is there any other possible edge case? Because if the time slice is down, we return the context. If not, we push it, we pop it, and we also have to check if there is a next, and if there's no next, we check the current, and we do. I think I have covered enough edge cases too. I'm not sure, but I believe it's done. So that's super simple code, and let's think about it from our IRQ. In our IRQ dispatcher, let's go back to our vectors. As soon as there is a EL1 IRQ, we save the context, we move that pointer to the top of the stack, pointer to the x0, which is the first argument to the function. we call the function, and within the function we actually check the current IRQ code. We switch between codes, and if the code is 27, we just call the timer handler and schedule on tick. And schedule on tick is just going to check if the current task has enough time slices. If not, it's gonna throw it away back to the queue. If not, it's just going to take the next one from the queue and run it. Here we get the context back from the schedule and we just send it back. No, we don't do anything, I guess. We get it. In this case we have to send it, and that's what we do. We just set context equal to the pointer that comes from schedule, and we break, and we are fucking done. That's super simple. Now we can try to run this code, I guess. Let's see if there's any other empty stuff we haven't yet. We have the biggest stuff, that is the syscall entry. Maybe we can make one thing work and then go to the next one, because debugging two things is gonna be so much fucking pain. What's schedule next? I think we don't need this schedule next. Yeah, that is what we do inside schedule on tick. We have IRQ dispatcher and we have the syscall dispatcher. Those are the two things that we need. And we have EL1 sync entry and EL1 IRQ entry. It's good. Maybe within EL1 sync we can do the same thing. We yank it and we paste it here and we remove it. Because even within EL1 sync entry we do the same thing. We have to, because if you are inside a sync entry, it's most probably a syscall. At least in our case it's just going to be syscall, because our users don't really do anything. They are just going to call a syscall and going to end it. Nothing much. I think we are good to go. And what the fuck is this code? Let's just think about it for a bit. What are we doing? We are reading from the special register. It's RS, that means it's read from special, I suppose. Let's see. rs register. No, instruction. That means move two registers. So I'm fucking wrong. Transfer content from program status includes move to register from PSR. It's correct, actually. I'm correct, because we read from the special register into our register. So it's correct. The special register is this, and we read into our, I guess it's correct. Move to register from PSR. PSR is the special registers. I think so. Yep. So we read from this ELR1. Why do we need to read from? Because we are coming from an from an actual function into an interrupt handler. So we need to go back to it. So we need to store that value into X10. And okay. Here what we are doing is that we are storing it into X10, and we are doing some sort of operation to check if it's a syscall or not. If it's a syscall, in that case we dispatch it. And how exactly this ESR ELR1 is gonna say anything about if it's a syscall or not? What's the hex code for SVC? SVC, right? Instruction, because SVC is supposed to be the that's what we use to trigger syscalls. So it's not this. It's 90 SBC, it's 9003F. Then what the fuck am I doing here? Maybe I'm going one step back. I don't know. I don't know. I don't know. What is LSR? LSR instruction. Logical shift right. So we are shifting right. Which what are the operands? Operands. Making it suitable for highlight. LSR. We move this and store it into R0. We move R0 and store it into this. Just give me an example of which is destination and which is input. That's all I need. I didn't ask anything. Operands. Okay, so this is source and this is destination. Okay, that's all we need. So this is source and we store it into destination, that is x11, and we shift it 26 fucking times. Why? We shift... No. How many times do we shift it? By 3 bits. 1 bit. Okay, so we shift it 26 times. Why? Why do we want to do that? And then we check if that bit is equal to 15. 0x1 5. What is 0x15? Is it 27? Hex to decimal. Not this. I don't like this interface. Rapid tables. 0x1. What's it? It's 20 fucking 1. What? Why am I comparing 21 here? I understand. If it's not equal to 15, then we say it's not a syscall. And if it is equal to, then we know that it's syscall and we just jump to directly syscall dispatcher. That's interesting. First of all, what is ESR EL1? ESR EL1 is supposed to be the return argument. Then why am I checking it from there? ESR EL1 typically by the operating system for diagnosing causes, storing the information describing the nature of the it's nature of the exception. Okay, then what is the return register? Just register that stores return PC in ARM during an exception, during an interrupt. What the fuck? It's just going to use link register. Oh no, I learned it bit different. Maybe was I wrong? I thought it's gonna use a special register and use that as the. Let's check. Holy fucking moly. And show the instruction written from handler. It's ELR EL1. Okay. I knew it. I fucking knew it. I was not wrong. I just was bit off because it all looked the same. So the as soon as the exception occurs, because I know, because I have written that code in my scheduler or in my context.h somewhere. Let's check that. Maybe if we just look. Yeah, see here, I'm storing that ELR EL1 because we need to go back somewhere, so we need that register. That's why I stored it. But in our case, we are reading from ESR, not ELR. Okay, so that's good. So I was half right and I was half wrong. So it's just that ESR EL1 is supposed to be the one that holds the information about the exception, and ELR EL1 is the one that is going to hold the actual written pointer, the written instruction. So that's fine. So if we read from ESR EL1 from this bit, and if it is 15, that means it's a SVC instruction, I guess so. Okay, then let's check ESR EL1. So ESR EL1, how do we know what instruction caused the interrupts? Yeah, ELR. Oh, by examining, there's another one thing called ELR. No, ELR is the actual one that you can go back. Okay. So maybe that's just instruction code. So if based on the code, we can know that if it's a syscall or not. Let's search for syscall SVC. We have some SVCs. And it's 01000. SVC instruction execution. It's 001. What are the other things? I think this is it, because in Art64 we need to use this. What is this? Go to bytes to, no, bits to hex. Oh, fuck me. Convert. It's 15. So it's correct. So we are actually inside the developer manual, and where we found something called the ESREL1's different informations that are stored in that register, and one of the information is the current executed instruction. And if we shift that 26 times, we should be able to reach this fucking instruction. And what is that? And it's encoding of all other exceptions from 0 to 23rd. And the exception class is from 26th bit to 31st. That's why we are moving 26. We are shifting to 26 so that the 26th bit will be in the 0th bit now. And then we can just compare it. And if it is 115, that means it's a syscall. If not, it's not a syscall. Maybe it's better to write it down here, because we can't simply explore this every time. It's better to just fucking write it down. And 31st to 26th bit is the one that holds the exception information. And so we shift 26 times to move the 26th bit to the least significant or most significant. I don't know, I fucking forgot, so we just say 0th bit. And our 0x15 is the SVC exception. SCV or SVC exception. That is the syscall. Okay. Now we have a little more information to look into the next time we see this fucking thing. And one more thing, this return will actually return whatever that was in ELR, EL1. That's good. Okay, that's good. What's now? Now we have to have to come back to the chain of thought I was doing previously. Now that we have figured out a side quest. Okay, so we have the EL1 sync entry, and we have the EL0 sync entry that is supposed to do the same thing. And we have the what do we have? We have the IRQ dispatcher. So let's just write the syscall dispatcher. Let's just, oh fuck me, this is just so fucking annoying. Sometimes I just don't remember if I'm in the insert mode or I'm in the visual mode, so I just don't know. I just press yank and it just writes on top of it. It's just fucking annoying. Whatever. So let's just write the next part. That's it. It's in the hand list. Let's see. No, it's not. It's not. It's not. It's supposed to be. What were we writing? We are writing here. Okay. Okay. Now we just wrote the timer handler. Now we need to write not the void, and we paste it, and we do. We need the context here. I think we need one thing here, that is the syscall number, because if we are gonna dispatch syscall, we need one thing, that's the syscall number. How do we get that information? Because right now we are not passing anything here, but we need the number. How can we get that information here? Uh, can we get the syscall number? I think in ARM, syscall number is stored in a register. I think so. Right? SVC instruction ARM. Oh, okay, we give the number as the first one. Then we need that number. Does ESREL1 store SVC syscall number? Yes, so it does store it. It's in which is stores the syscall section immediate operand, which says syscall in the lower 16 bytes. Okay, so let's go into the developer handler and see the first 16 bits. This is ESREL1, and the first 16 bits till this, and it says a lot of stuff. And where is the syscall? I don't see it. I don't fucking see it. Oh shit. So maybe if in case the actual syscall is SVC, then the rest we can just not think about the rest and just take the first 16 as an value. I don't know. Ta-da, ta-da, ta-da. I don't know. I don't know. I don't know. I'm still looking for something that's saying that 0 to 16, something like that. Ah, value of the immediate field from the SVC instruction. So it's 0 to 15. That's correct. Okay. So we can just take 0 to 15. We can shift it again. So what we can do is that we copy this instruction, we shift it to, now 0 to 15 is already shifted. Now we just have to remove the upper bits. No, we have to hex the upper bits. So what does that mean? So we have to AND with FFFFFFFFF without the last two F's. And what's the total size of this register? It's only 24. Okay, so we need to zero the top 20, 0 to 16 to 24, or we just take 0 to 15. Is there any way to take 0 to 15? Read from a register into another register. What the crap? I think there's no such operation. We have to chain multiple operations to achieve that. Or no. How can we do that? If only we knew ARM instruction better. But we could do, what we could do is that we can right shift 0 to 15 to the end, so the first bits will all become 0, and then we can left shift it back to 0, so the top bits will be 0. That is possible, but that would be the least efficient way to do it. There must be some better way to achieve this, so let's learn that, so it will be useful in the future. Let's just type read bits from register. Probably this would be general enough to come up. We used to set 0 black based on the bit state. No, read bytes then. I guess with load register we can achieve that. With load instruction. We can. We don't need this. We need pair of registers, so it's LDP, load and store address, and we have to store What? To address? Fuck me. Oh, this is address. I don't want to read from address. I want to just read from. I didn't understand any fucking thing. Maybe I'll just do my shift operation. That's the fastest thing to do. What we can do is that let's use x10, x9 and store move. Okay, I have to do right shift. It's left to right, so right to left. This is right, left to right. Have to do the opposite. Oh, fuck me. Mm-hmm. Read lower half from an 64-bit register arm. Oh, okay. So if we use D0, this is what we need. We just read H. What? Am I correct? If we read H11 move into x0 H11. I hope this is correct. If this is what we call it as, if we call it as H11, then we should be reading 16 bits from the R11 register. Let's see if it's correct. Least significant bit, that is the 16 bits. Is there H? I think this is correct. I don't know. It at least someone has wrote it down like that, so I believe it's correct. But here I don't see that hutch. Maybe it's not there, maybe it's there. I don't know. I think it's there because even where the fuck is hutch? Hutch 0. Oh, here. Oh, floating points. I think it's good. I think it's good. It should work. So we'll pass take the lower 15 to 0th bit into x0. Now we have the syscall number and we call the syscall dispatcher, and we can have it as uin64 syscall num, and let's just print it as of now. U of print f, and what is it? Syscall number. Let's put D. No, I have L. This is my own format descriptor, so don't get me wrong. That's it. But internally, all it has to do is that it's just going to be again a switch. Expression would be the syscall, and if syscall is, let's say 5, then we put kmalloc. What about other arguments? Oh shit. But in general, those arguments should be stored from x1, right? Where do we store the argument passed to SPC instruction? No. What? Arguments go in register R0 to R2. Yeah, that's it. So we can just read from. So in that case, I should not overwrite x0. Okay, and then I'll just overwrite x9. Oh, shit. How exactly am I gonna pass that syscall number to syscall dispatcher now? Oh, it's simple. I just move into R3. So it's R0, R1, R2. So there will be three arguments most probably. So we use R3, X3 as X0, and then we can move X0 to so the first argument will be syscall number. Second arg will be the first argument. No, second one will be the second one will be the actual second argument. Yeah. So we can move. We just need one temp, and then we can move everything properly. So it will be move x4 equal to x1, move x5 equal to x2. Now we can move x1 equal to x3, x2 equal to x4, and x3 equal to x5. That's it. Now we have the first argument, the second argument, and third and the fourth. Now we have everything. So the syscall dispatcher will have the it will be uint. It will be void. So whatever it depends on the syscall, they can interpret it anyway. So we'll just put it as uint64. arg2 and uint64 arg3. That's it. And we can call kmalloc. If it's 5, we call kmalloc with arg1. That's it. And we return a pointer uint64. Okay, how am I gonna return something from it? I also have to think about that. And it's going to return pointer. So everything is going to be, maybe it's better to just return a void pointer. Even here we can just return it as uint64. And the actual person in the top can think about what it is and do the rest. Yeah. Results. Results will always be UN 64. 64 results. Results will always be returned. This way the user can interpret the output based on what they are calling, because that's what libc does. Because we have a low level in Linux, we have the low level helper called syscall something, and the actual syscall, the like example write, will internally call syscall, but between that it's going to interpret the data by the libc. Those not the syscall. The syscall is just a basic helper. The libc will do the actual implementation to interpret the outputs and stuff. Okay guys, right now we have let's just write holy moly. We have the code for IRQ and syscall dispatch, and also we set up the finished vector setup. I think, yeah, I think that is good. It should be it. Okay, I think it's done. Okay, I'll continue this later, guys. It should be good. It should be good enough for one session. Thank you. Have a good day. Bye.